Dr. René Voigt. He's leader of Environment and Health at Ford Research and Advanced Engineering Europe. And he's responsible for the development of advanced measurement methodologies, environmental impact of vehicle emissions, RDE and non-regulated emissions, as well as health and wellness trends and technologies. Dr. René, thank you very much for joining us. You have a presentation now on RDE, NOx and PN measurements. So thank you very much.
Thank you very much for the introduction. Yes, indeed. I will talk a little bit about variability, so this error margin, which Penny already mentioned, and then I raise the question, what is the impact on the air quality, really? So we'll have done that prior, and we have now done a new study with new emission factors, with the most updated emission factors, and I will show you two scenarios how the air quality will impact. So first of all, NOx and PN measurement variability. A little recap what has been done there, and then air quality projections from today to 2030, and as I said, air quality impact scenarios where we will simulate the impact of a potentially changed error margin, how a lowered conformity factor would impact or not impact the air quality. And the other scenario, I come back to that, is an environmental zone. So please stay with us. It's quite new stuff I present here. So this is one of the studies investigating the PEMS variability. Picture is taken from the Karlsruhe Institute of Technology. They, together with German OEMs, were measuring 4 different vehicles. And the interesting thing here is that we put 2 PEMS kits inside the same vehicle and have them running in parallel on the same vehicle on the public road, and compare and learn really what do the 2 instruments show for kind of results. This is how the equipment looked at Ford. You can see here the 2 PEMS instruments fitted, so 2 PN PEMS. Our focus was really on the PN PEMS variability. So we placed the Karlsruhe Institute instrument into the vehicle and put our own instrument also in the vehicle, and we have 2 independent exhaust flow meters, so everything entirely independent to compare the 2 setups against each other. And I just briefly touch really the results here. This is just gives you an indication what the 2 analyzers will show. So altogether, they record, of course, the NOx spikes during the acceleration or the higher load situation. So these are Euro 6 vehicles. It's not really important what the readings here are. These are not Euro 6 detemp vehicles at that time. It was just regular Euro 6 vehicles. But you can see here that the instruments catch the spikes of the NOx signal. However, even from the qualitative picture, you can see that there are differences in the concentration readings. And the same thing you see here with a 0 reading. So we start at very identical levels, and then during the course of the test, one instrument obviously drifted, and that leads to an error. So altogether, there's evidence that there's substantial error margin, both between the peak concentrations and also the 0 drift occurs. And that is all with instruments which have been calibrated and properly treated before the test. Now, with respect to particle number, same situation occurs. So we have here the 2 instruments in one of the vehicles. The vehicle is not equipped with a particle filter. It's somewhere written there. It fulfills, it has in the order of 1 times 10 to the 12 particles per kilometer. One instrument reads here 1 times 10 to the 12. The other about half or 50% less at 8 times 10 to the 11. And that comes not only in the urban rural motorway, but it shows essentially everywhere. We investigated this, what could be the cause there, and one evidence was that also the CO2 levels measured by the instruments had the same deviation, and that led us really, so we have here the reading compared the CO2 to the ECU reading. One instrument showed in the order 30% higher CO2, the other showed 20% lower as compared to the ECU reading, so the fuel consumption onboard reading. And it turned out that indeed the exhaust flow meters show different exhaust flow. So that translates into a wrong CO2 fuel consumption reading, and that translates also explains the different NOx and, as shown here, the particle number readings. So although these instruments are all well maintained, are calibrated, there is substantial variability, and there's really a need to standardize this measurement instrumentation. And of course, we're very much interested in the SEN activity because the laboratory tests, the laboratory particle number, or the laboratory PEMS comparison to the CVS, that is good, but on board, on site, on the vehicle, you have vibrations, you have temperature gradients, and that all needs to be captured. The Karlsruhe Institute of Technology did a very systematic investigation on all the different factors affecting now this error margin, and that can be the analyzers, it can be the ambient situation like the humidity or heat build up, the error in the ground speed in the GPS signal, the exhaust flow which I mentioned, and for example, exhaust flow is this one here. So for example, vibrations or temperature gradients which might occur during the test, and that all impacts the results. And the Karlsruhe colleagues, they did a quantification and assigned errors to all of the different factors, adding up to, in this case, 30 or 29 milligrams per kilometer. However, that only covers some of these potential errors. And for example, it would not cover the entire error of the exhaust flow meter. So we conclude that at the time being, this 0.5 of a conformity factor error margin is very well justified. It can be rather larger than lower, but there's still some work to be done, and this activity will start. Now the question is, of course, what is the impact on the air quality, and how will the air quality, both with respect to NO2 and PN, develop in the future? And of course, this builds upon Jens Borken's presentation, which he gave yesterday, and is very much related to that. So our simulation is much more specific to a certain pollution situation. So the modeling approach is different to what YASA is doing. We concentrate on an air quality station, have a very well defined fleet composition here. We have very well defined emission factors, and use background air entering this box, and then calculate the air quality at this location. You can imagine that an air quality measurement station is located here inside this box. So the first thing one needs to do these kind of simulations is to have a good knowledge of the fleet composition. We do that for 3 locations, Stuttgart, Düsseldorf, and Cologne. And you can see here the fleet composition in the year 2016, where we start. So we have 50% of gasoline vehicles, and then the reddish colors diesels. This considers already a dynamic fleet composition, which means that the diesel vehicles are driven or operated more than the gasoline, which adds here to the 50% of the mileage by the diesel vehicles. And then when you continue with the time, you can see that the old emission classes, so let's take an example here, the Euro 4 and 5, this is the Euro 5 vehicles, they become smaller, while the composition or the contribution of the vehicles by Euro 6 and then Euro 6D temp and Euro 6D, they will propagate into the fleet and then are taking over the mileage driven at the different locations. We have so far simulated three cases. The base run uses the latest emission factors from the handbook of emission factors. This includes now the increased NOx emissions at the lower temperature. So it has been found that, or has been considered in the handbook now, that there's an increase of NOx emissions with lower temperatures. Something like we saw yesterday, this increase with the Euro 4, 5, Euro 6D vehicles. And Professor Hausberger provided, so these numbers, he also provided numbers for the gasoline vehicles and also an update for PM and PN emission factors for the gasoline vehicles is included. And then the fleet composition I just described. Then we have two scenarios. One is a hypothetical assumption that the error margin would be put to zero. So some people believe that if the error margin is set to zero, that then the emission factor would also, or the real emissions would potentially decrease by this factor of 0.5, which is essentially not true, because the manufacturers, they need this emission factor, this error margin, to cope for the variability coming from the measurement system. And that's maybe also one reason why we see already these low emissions, because you have to consider the 0.5 which someone else could have when doing the PEMS measurements. But still, for this exercise, I assume that the emission factors or the conformity factor is decreased by 0.5, and therefore we hypothetically assume that the Euro 6D conformity factor would be then 0.5 lower, and for Euro 6D final the same thing. So we multiply the emission factors which are in the model by this ratio here. The scenario for the environmental zone is quite interesting, because here this has been discussed in Germany and is partly being implemented, that all diesel vehicles up to Euro 5 are banned from the street. We have some exceptions which just naturally occur, and the traffic volume is kept constant. So it's not assumed that you reduce the traffic amount, but this is then replaced by clean Euro 6D temp or Euro 6D final vehicles or gasoline vehicles. First thing is the result is what happens with the NOx emissions. The NOx emissions are calculated for the fleet. Each fleet has, under the given traffic situation, has an emission factor, and that adds up all to tons per kilometer per year for the street. And here for Stuttgart-Neckartor, you can see that the emissions are projected to come down substantially. This is mainly due to the removal of the Euro 5 passenger diesel vehicles, but also the gasoline vehicles. So these bluish colors here, they are being cleaned up, and the heavy duty also contributes here. So you go down for all the simulated traffic situations, and this is due to the replacement in the fleet by Euro 6D temp and Euro 6 vehicles, which then have, let me see, have here the contributions these are the Euro 6D final and Euro 6D temp emissions. This is still the Euro 6 diesel vehicles, which are not made for the RDE emissions. So the elevated, some people call it, emissions for the Euro 6D non-RDE vehicles, that's all considered here in the model. Then we'll put this into the box, add the incoming air from the background, and calculate on a daily basis, no, actually on an hourly basis, the NO2 concentration, and do finally the averaging over the months and over the year, and report the annual mean NO2 concentration. And we start here in Stuttgart today at about 80 milligrams. So these are the non-compliant, it's a non-compliant situation. New here in this study is also the Cologne Clevische Ring simulation, where there's about 65 in that order, so non-compliant situation. But the good news is that that over the time, essentially at all traffic situations, the NO2 targets will be reached, the 40 micrograms will be reached. That is the case for Stuttgart-Neckartor, maybe not quite, but for Düsseldorf, we project to reach it at 2025. Cologne in the same time frame. So also the hotspots will be compliant. And yeah, okay, let's leave it. Interesting is maybe also the projection. Which are the contributors to the NO2 air quality? And this is shown here. So the greenish bars are the urban background contribution for the traffic hotspot. So you have substantial concentration contributions from the urban background. Of course, in the urban background, there's also contribution from the traffic included. Here you see, yeah, then the contributions of the Euro 6 vehicles, and then the contribution of the Euro 6D temp and Euro 6D vehicles, very, very small. I mean, they contribute also a little, yeah, stripe in the background concentration, of course. But, so you see that we project that the fast fleet renewal, or a fast fleet renewal of Euro 4 and 5 is needed to achieve the air quality targets. For particle number emissions, we looked, as I said, we did the same work now for the particle number emissions. So we assigned to the different fleets, for the different vehicles inside the fleet emission factors, and add up the particle number emissions. In 2016, we have this amount of particle number, contribution approximately half by light gross vehicles, so transporters and heavy-duty vehicles. These are still the non-particle filter vehicles. And here the Euro 3, 4, and 5, no, 3 and 4 vehicles, they contribute substantially. And then the Euro 6 vehicles, due to the and also the Euro 5 vehicles, due to the introduction of the particle filters, have a very small contribution. Indeed, this is maybe even an error in the handbook of emission factors. So these are the Euro 5 diesel vehicles, and I would think that the emission factor in the handbook is still too high for the Euro 5 DPF vehicles, because they have essentially also zero particle number emissions. So maybe it includes tempering or whatever. So you can discuss if that is really the right number. But what the focus of this presentation is on, what is the contribution of DI gasoline or of gasoline vehicles? And these are the bluish bars here. And you can see that altogether the particle number emissions will come down very substantially due to the fleet propagation of particle filter vehicles. And also the gasoline contribution also due to the introduction of the RDE regulation that will be and will stay at a very small contribution. For the air quality, I don't show the modeling here. This is from the former study. We estimate approximately 4% of the particle number from the gasoline vehicles. So just to keep the numbers right here. Now 2 slides on the air quality impact scenarios. So as I said, we so far looked at the base run here. And this is the hypothetical case that the conformity factor is reduced by 0.5. You can see here, as compared to the base run, there is a little impact compared to here. But this impact coming from here to there is really marginal. So the major step comes really from changing to the RDE regulation, which brings down the emission 80% in that order. And if you then have a little bit further, yes, you can see this within the noise, but I think this has only a very small impact. On the other hand, an environmental zone has a very substantial impact. You can see that, let's see here, starting from the base case down to the environmental zone. Now the Euro 5 and Euro 4 diesel passenger vehicles are taken out of the fleet, and that shows then, of course, in the results of the environmental zone. In the end, in 2030, of course, the difference is not that big anymore because then the fleet propagation has occurred. So let's skip that one for the time being. Now, the interesting question is, of course, these are now, what I showed so far are very dedicated air quality situations, very specific simulations. How does it look for the overall station? So what we do is we put all the measurement stations here in one line just by increasing NO2 numbers, have simulated these situations, and come down now with the model to these concentrations, as I showed before, and do an extrapolation, and now count the number of air quality stations which are above the 40 micrograms. So here in 2016, these are 160, and then this cut point goes further down, and as you can see here already qualitatively, in 2030, there are there's only one station in the model, which is the Stuttgart-Neckartor, which is still above. And this is then the summary chart of that. Today we have about 60% of the traffic. This is only talking about the traffic situations above the 40 micrograms. And then you can see here the impact of this conformity factor change of the hypothetical 0.5 reduction, and then the impact of the environmental zone is of course quite substantial, but still with the environmental zone, which can occur more or less immediately. There are situations where there are still exceedance of the 40 microgram. In summary, the measurement variability is still quite substantial. So far, a factor of 0.5 or 0.43 is well justified. We did air quality simulations with latest emission factors, also for the particle number, and show that the overall decreasing NOx emissions will lead to substantial NO2 air quality improvement or reduction of the exceedances with close to 100% compliance in 2030. Particle number reduction in the order of 88–90% as compared to 2016 due to the introduction or the rollout of the non-particle or replacement of the non-particle filter diesel vehicles. The contribution of DI gasoline relatively small. Largest reduction by fleet renewal with Euro 6D and Euro 6D temp vehicles, and the environmental zone has also quite an impact. Okay, I'll leave it here, and I'm open to your questions. Thank you.
Thank you very much.